Welcome back to the Explainer. Today we're getting into a deep dive on TypeScript mastery, specifically tracing the evolution of type safety. We're going to go all the way from defining basic, foundational data shapes right up to implementing bulletproof global project rules. And we'll be doing all of this by looking at concrete code examples so we can really see how TypeScript operates under the hood. Here's our roadmap for this explainer. We're hitting advanced data structures, classes, types and interfaces, utility types, the whole any versus unknown debate, and finally, enforcing strict rules. All right, Section 1, Advanced Data Structures. Okay, let's kick things off with tuples. If you're used to standard JavaScript arrays, you know they're sort of the Wild West. They can hold anything and grow to any size. But a tuple fundamentally changes the game by locking in both the length of the array and the specific order of data types it contains. It's basically the perfect tool for when your data structure is completely fixed and known in advance, like when you need to return multiple specific values from a function. Take a look at this syntax. We declare our pair variable and explicitly type it with square brackets as string, then number. Once you assign it the array containing score and 100, you are put in a rigid box in the best way possible. You absolutely cannot flip the string and the number around, and you definitely can't add a third item to that array. If you even try to assign 100 first and score second, the compiler is going to throw an error immediately. It strictly guarantees your exact data shape. Moving on to enums. Now here's a fascinating fact if you're coming straight from vanilla JavaScript. Enums are actually one of the very few TypeScript features that exist as real, tangible objects at runtime. They aren't just a compile time check that evaporates when you run the code. They let you define a set of named constants, which is an absolute game changer for documenting your intent or handling distinct cases, like specific user roles. So TypeScript gives you two main flavors here. Numeric enums give you auto-incrementing values, starting at 0, then 1, then 2. These are super handy for simple, distinct cases where you really don't care what the underlying number is. String enums, though, require each member to be constantly initialized with a string literal. And honestly, they are fantastic because they serialize so perfectly. Let's be real. When you're debugging a raw JSON API response, seeing something like role admin is a million times more helpful than just seeing role 2. Which brings us to the ultimate TypeScript debate, the one that happens in almost every single development team. When you are structuring your objects, should you use a type or an interface? Let's settle it. Section 2, Classes, Types, and Interfaces. Real quick, before we pit types against interfaces, let's talk about classes. When you're building classes that inherit from a base class using the extends keyword, like this dog class extending our animal class, there's a strict, absolutely vital rule. If your derived class has a constructor, you must call super.inside.constructor before you ever attempt to access this or any of its properties. That supercall runs the base animal constructor, laying the foundation down before you start slapping on the dog-specific details. Now, interfaces actually map pretty closely to that whole class-based vibe. An interface is a first-class primitive built specifically for defining object shapes. And just like classes, they can inherit from other objects using that exact same extends keyword. Very OOP-inspired. But what you might not know is that this inheritance model comes with a very specific performance quirk. Check this out. Using an interface with that extends keyword actually gives the TypeScript compiler a slight speed advantage. The compiler can cache that interface by its name in an internal registry. On the flip side, if you try to achieve the exact same inheritance using a type alias combined with an intersection using that ampersand symbol, it's actually slightly slower. The compiler can't cache it by name in the same way, so those intersection types are basically recomputed nearly every single time they are checked. Even with that slight speed advantage, though, we still highly recommend defaulting to type for your everyday object definitions. Why? Predictability. Interfaces with the same name and the same scope will secretly merge their declarations. Imagine you define a user interface, and some third-party analytics library also defines a user interface. TypeScript just silently merges them. Suddenly, your app's user object is throwing errors because it's missing analytics properties you never even wrote. Plus, types have implicit index signatures and can express unions and conditionals, which makes them vastly more flexible. So, default to type unless you specifically need that extends behavior. Okay, but what happens when you have a perfect type already defined, but for one specific API call or function, you just need a slightly modified version of it? You definitely don't want to copy and paste the whole definition just to change a single field.
That leads us right into Section 3, TypeScript utility types.
Think of utility types like math operations for your code. Take partial. If you pass your user type into partial using angle brackets, bam, every single property becomes optional. Absolute lifesaver for a profile update function where a user might only submit 1 or 2 fields. On the flip side, required makes everything mandatory. And read-only? It ensures that once an object is created, its properties cannot be reassigned. It functions a lot like object.freeze in JavaScript, but it's strictly enforced right at compile time. Then you've got pick and omit to actually sculpt your data. Say you've got a massive database user object with passwords and internal IDs, but you only want to send the username and email to the front end. You literally just use pick with your user type and specify those exact keys. Or you can use omit to keep everything except the password. They let you carve out the exact data shape you need from a much larger source, which keeps your code incredibly clean and DRY. So everything is super strictly typed until you hit the real world. As we move up the ladder of abstraction, we have to figure out how to safely handle dynamic, totally unpredictable data, like an API response where we just don't know the shape in advance. Let's get into it. Section 4, any versus unknown. Let's be clear up front. Unknown is the much safer counterpart to any. When you type a variable as unknown, you are explicitly telling the compiler, hey, I have no idea what this is yet. And because of that, TypeScript steps in and forces you to explicitly check the type using something like typeof or a custom type guard to literally prove what the data is before you actually execute any operations on it. And here is the absolute most critical point. Using any essentially turns TypeScript off. It bypasses the type system completely, allowing you to call whatever methods you want. Sure, it feels easy, but it massively weakens your architecture and heavily risks unexpected runtime crashes. We've all felt the pain of debugging a crash caused by an implicit any slipping through the cracks. Unknown, on the other hand, maintains your compiler safety. You can assign anything to it, but you literally cannot use it until you prove what it is. Just looking at the breakdown, any gives you absolutely zero type safety, while unknown enforces rigorous checks. Honestly, any really only belongs in legacy JavaScript to TypeScript migrations where you just need the compiler to quiet down for a second while you convert files. But for modern code, handling raw APIs or user input, you should strictly use unknown to handle external data safely and force yourself to write the proper validation logic. Finally, Section 5, enforcing strict rules. Because everything we've talked about, it's all governed by the brain of your project, your tsconfig.json file. By simply going in and setting the strict flag to true, you are flipping a master switch. This single Boolean enables a massive range of type-checking behaviors. It ensures things like implicit any types throw errors, null checks are strictly enforced, and it fundamentally guarantees program correctness at a structural level. So I want to leave you with this thought as we wrap up this explainer. TypeScript is really only as safe as you configure it to be. No matter how advanced your code is or how beautifully you've sculptured your utility types and classes, your safety net relies entirely on that configuration. So your immediate action item? Go open your code editor right now and make sure that strict flag is turned on. It really makes you wonder, how many hidden bugs is your current configuration hiding right now? Thanks for hanging out with me for this explainer and keep building robust code.